Well, good day, ladies and gentlemen, and let us continue. We are in Unit 6, and we are discussing reactions. And let's do a quick overview of reactions, okay? We're talking about chemical reactions. We talked a little bit about what chemical equations, which are representations of reactions, and we talked about types of chemical reactions, and the first type we talked about was a synthesis, and we said that is A plus X, and that yields AX. That's the general form, and there are 5 types of synthesis reactions and that we want to learn, and then there's decomposition, and we said decomposition is essentially the opposite of synthesis. So it would be the general form is AX yields A plus X. And what's interesting here is I have 2 things in synthesis and we form 1 thing. And in decomp, we start off with 1 thing and we form 2 things. And so that's kind of the way we can identify these things. And then we learned about combustion. Combustion is where we have fuel that reacts with an oxidant. And for our cases, we really are looking at some kind of hydrocarbon, something with C and H in it, maybe O in there too, plus oxygen. And that's always for us going to yield O2 and H2O. And that's because we're assuming this is complete combustion. And then the 4th type that we talked about was a single replacement reaction. And in that case, the general form is I have something that is by itself, and it is going to react with something that is aqueous in a compound, and it's going to replace that. And it's either going to be a metal replacing a metal, or a metal replacing hydrogen, or it could be, a halogen. If this is a halogen, it will come over here and replace a halogen. And the key to understanding this is we have to remember that we have to check out something called our activity series to see if our metal will replace another metal. And remember, it's only the more active metals, you might call stronger metals, that will replace other metals and hydrogen. And there is an order, there is a priority in terms of replacement of halogens, right? Good. So those are the first 4. And now let us talk about the last type, and that is changing color. Double. Oops, is that double? That looks like 2. Yoink. Let's go with double replacement reactions. Okay, so we want to learn about double replacement reactions. Let's start off by looking at our consider. Consider mixing solutions of silver nitrate and sodium chloride. Okay, what's different already about this? What are my reactants? Well, my reactants are all solutions. Okay, that means they are both compounds. So what's our general form? Well, the general form for my double replacement reaction is that I have AX plus BY yields, what do you think? Well, A is going to come over here, and B is going to come over there, right? And so I'm going to make BX plus AY. And I like to think of this as the post-prom reaction, right? We have couple AX, and they are doing fine until prom, and then they get into a fight during prom, and then BY is the next couple, and they're doing fine until prom, and then they get in a fight, and so they start to break up, but neither A nor B or X nor Y want to be alone. So A comes over and takes the new date Y, and B comes over and takes the new date X. So I call this, or I think of this as the post-prom reaction, right? Good. Now there are 3 types that we want to learn about. Type number 1 is what I call formation of a precipitate. Precipitate. Good. And so what that means is I'm going to have something like sodium chloride, aqueous, plus silver nitrate, aqueous. And now notice, when I have a double replacement, I've got a compound made of 2 things and a compound made of 2 things, right? 2 ions. And it's possible I may have more, but it's always a compound and a compound. Whereas up here with single replacement, I didn't have a compound, and one of my things was just a element, right? It was just a metal or just a halogen. Down here, I have a compound and a compound, and then what am I going to do? These are going to trade places, so I have my sodium coming over here, and my Ag coming here, and so I'm going to make sodium nitrate plus silver chloride. Now, I have to decide my states, okay? And so one of the little stars here is we need to do what? We need to check solubilities. Hey, you guys remember that? We learned earlier about solubilities, and I said they will become important. So, just a refresher, here's our solubility guidelines. These are things that are usually soluble. These are things that are insoluble. What did I make over here? Oops, what did I make over? Oops, what did I make over here? We'll find it eventually. I made sodium nitrate and silver chloride. Well, what do we know about nitrates? Nitrates are soluble. If they're soluble, that means this will be what? If it's soluble, that means it's aqueous. Silver chloride. Let's look. Do we have anything on silvers? No. Do we have anything on chlorides? Here's a chloride. These are soluble except, ooh, look at that. What does that mean? It's an exception to the solubility, which means silver chloride is insoluble. And if it's insoluble, that means it forms a precipitate, a solid. Got it. Okay. So, Mr. Smith, are you telling me I really need to know that solubility table and memorize it? Yes. I'm telling you, you really need to know that table and memorize it. Because there's a funny thing, folks, with my double replacement reactions with this formation of a precipitate. If I have an aqueous plus an aqueous, and it yields to an aqueous plus an aqueous, you know what we call that? We call that a no reaction. If I have two aqueuses and I form two other aqueuses, that is not a reaction as far as we are concerned. We say that is no reaction. So you have to find out, do you actually form a precipitate? Okay, good. Let's move farther. Let's see, did we just do this one? Yes, we just did silver nitrate. We said, hey, I got AgNO3. I have AgNO3. It's a solution, so that means it's aqueous. Sodium chloride, it's a solution that's aqueous. These guys are going to switch around, and I'm going to make sodium nitrate. And we just we recalled that nitrates are all aqueous. And silver chloride, we checked that out. We said, hey, that forms a solid, so it's a precipitate. So this is my beautiful double replacement reaction. You guys try to do this one. Okay, so what do? I have potassium carbonate and magnesium acetate. They are both solutions. Okay, potassium carbonate, and it's a solution, aqueous, plus magnesium acetate. Boy, I hope I memorized all my polyatomics. I hope you did too. Good. And what's going to happen? This is going to go and what do I form? Magnesium carbonate, right? Magnesium's a +2 and carbonate's a -2 plus potassium CH3COO, two of those, potassium acetate. So we need to do what? Figure out the states, because we're not sure if this is a reaction yet. If these are both aqueous, then we'd say no reaction. Good, so let us go to our solubility table. Acetates. What do we know about acetates? Well, here's acetate, and they are what? Soluble, and what are the important exceptions? None. So that means my potassium acetate is aqueous. You know, there's another way I knew that was aqueous, because potassium is a group 1, right? And we know that all group 1s are always soluble. Good. What about magnesium carbonate? Let's go back. We need to check out our carbonates. Now, where are carbonates? Here is carbonate. Carbonates are insoluble except ammonium and alkali metals. That's group 1, right? Is magnesium a group 1? No, it's not. So that would mean this is insoluble. My magnesium carbonate is insoluble, so I put an S there, and woohoo! We have done it. We have conquered once again. Everybody wave your hands. Good. Moving on. Here you go. Let's try another one. You all tried to predict mixing solutions of zinc sulfate and ammonium nitrate. Bring me back when you're ready. Well, here we go. Ammonium nitrate. That's a pretty looking compound, isn't it? Aqueous plus zinc sulfate. Zinc sulfate. Aqueous. It's going to form what? Okay. Yeah, na 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 na. And I'm going to form what? Zinc. Now, zinc is a +2. Sulfate is a -2. That's cool. Oh, we just had sulfate. Zinc is going to hook up with what? Nitrogen, but I mean nitrate. But nitrate is a -1, so that means I need 2 of those nitrates. And then plus what? Ammonium. Ammonium is a +1. Sulfate is a -2. So how many ammoniums do I need? I need 2 of those dogs. And now we need to check out their solubilities. Nitrates. Oh, we know nitrates, right? We should know nitrates. All nitrates are soluble. Yeah, na, 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 na. Good. So all nitrates are soluble. So that means this zinc nitrate is aqueous. Yoink. And what about my ammonium sulfate? Go here, look at stuff. I see sulfates. Here's sulfates. Sulfates are soluble except hey, sulfates are soluble as well. Not only that, we know that ammoniums are all soluble. That's an easy one. If you see ammonium, you know it's soluble. So that means this is also soluble, meaning it is AQ. Oh, what did we say? Aqueous, 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 aqueous. What's the answer here? The answer is no reaction. And that means I don't even have to worry about balancing it. I can just write down no reaction. Yay! Good. Moving on. We're going to mix solutions of potassium carbonate and hydrochloric acid. Potassium carbonate and hydrochloric acid. Okay, we have something else going on here, right? I have an acid, so that must mean there is another type of double replacement reaction, and there is. And it is, I like to say, 2 dot formation of a gas. All right, now there's several, but I want you to know 2 formations of gas. First of all, there is a carbonate plus an acid. Got it? A carbonate plus an acid. And whenever I have a carbonate plus an acid, I'm going to form carbon dioxide, gas, there's the formation of my gas, plus water, plus a salt. And remember, what is a salt here? What we're meaning here, it's just an ionic compound. And it's really the ion, the cation from the carbonate with the anion from the acid. That's what's going to be my salt. Okay? So here we go. What did we have? We had, I had potassium carbonate. Okay, so let's draw this here as our example. I have potassium carbonate, K2CO3, aqueous, plus hydrochloric acid, aqueous. What's going to happen? I'm going to form carbon dioxide, CO2 gas, plus HOH liquid, and plus my salt. Now, what's my salt? My salt's going to form between Cl and K. Well, K is a +1, Cl is a -1. So how many of each do I need? 1 and 1. Now what do we have to do? We have to balance this puppy, right? Oops. Let's clean that up. Yoink. How many K's do I have? I have 2. Okay, which means now I need 2 of these. All right, now it's balanced. So this is a carbonate plus an acid forms a gas. Now there's a second reaction, and that is you have a sulfide plus an acid, and that is going to form a gas, but it's going to be H2S gas plus my salt. Okay, so sulfide would be, something that has S2 minus, and then you're going to need two of those acids, and it's going to form your H2S gas plus whatever is the anion and the cation forming my salt here. So we could put, we'll call that X and we'll call this Y, right? And so my salt would be XY. Got it? Cool. And we could take something like, let's take solid zinc sulfide plus hydrochloric acid is going to form what? Well, it's going to form H2S. We're going to need two of those then, right? And that's going to be a gas plus my zinc chloride, right? And zinc chloride, well, you know what we have to do? We'd have to check out our solubilities. Chlorides are soluble except those guys. I don't see zinc, so that would mean this is aqueous. Now remember, do we have water present? Sure we do. There's water right there where we say aqueous. Good. So this is my other type of formation of gas. And what was given here? Hydrochloric acid, potassium carbonate. Let's do that. Hydrochloric acid, aqueous. I need two of those plus potassium carbonate. And I need one of those. I'm going to form carbon dioxide gas plus water plus two potassium chlorides, aqueous. All right, here, you guys do this one. So we're doing ammonium sulfide plus chlorous acid. Hey, I see acid. I see that these are AX. Oops, I see these are AX and BY, so I know it's a double replacement. I notice that it's an acid and sulfide. Aha, it's going to be formation of a gas. So here we go. Ammonium sulfide. Hey, my ammoniums are +1, my sulfides are -2. It's aqueous. Plus chlorous acid. Chlorous comes from what? Ite. Chlorite. That's ClO2. Okay, HClO2. Aqueous. What am I going to form? H2S gas plus a salt, and my salt is going to come from this and that, meaning I'm going to form what? Ammonium chlorite. Wow, that's a strange one, isn't it? There we go. And we need two of these, and we need a state. All ammoniums are soluble, so it's aqueous. There we go. How many of you got that right? That was a tough one. All right, the last two slides. Consider mixing solutions of sodium hydroxide, that's an AX, right? And bromic acid, BY, and we're going to predict. Okay, this is going to be the third type of double replacement reaction. So let's finish this up. We need the third type is something that we call an acid-base reaction. Acid-base reaction, aka neutralization reaction, aka, just to keep parallels, we had what? Formation of solid or precipitate, formation of gas, and this would be also known as formation of what? Well, every time we have an acid-base reaction, we form water, at least when we're having Arrhenius acid-base reactions. So this is formation of a water. And you have an acid plus a base, and that yields water plus my salt. So we can have hydrochloric acid plus sodium hydroxide. And what are they going to form? Well, my H is going to come over here. My Na is going to come over there. I'm going to form HOH, liquid. And what's my salt? Well, what's left over? Chlorine and sodium. So sodium chlorine, sodium chloride, and we know that chlorides by and large are aqueous. Cool. All right, let's do it. Sodium hydroxide, NaOH, aqueous, plus bromic acid. Hey, it's not hydro, so that means it's an oxy acid. So that means it comes from bromate, one hydrogen, there we go, aqueous. And what's going to happen? My sodium's going to come over here. My hydrogen's going to go over there. I'm going to form HOH, water, plus what? Sodium bromate. We know that sodium is a group 1, and all group 1s are soluble. There we go. Woohoo! Raise the roof. Finally, you guys do this one, and we are done. I have barium hydroxide. Here's my barium hydroxide. Hey, barium's a +2. I need 2 hydroxides then. Aqueous plus what? Chloric. It comes from 8. That means I need to have chlorate. Chlorate is what? ClO3 minus. So it's 1 minus, so I need 1 hydrogen. That is aqueous. Yields what? Okay, my barium's going to come over here. Oops, not that. My hydrogen's going to go over there. I'm going to make HOH, but notice I have 2 hydroxides, so how many hydrogens do I need? I need 2 hydrogens, so I'll make 2 waters, liquid, plus what? Well, then I have barium, and I have ClO3 chlorate, and I have 2 of those puppies, right? 2 chlorates. Chlorates are -1. Bariums are +2, so I need 2 good. So now the question is, what is my solubility of chlorates? Let's see, does it have it listed here? Probably not. No, it doesn't, but I know that chlorates are mostly soluble. So you don't have to know it, but I know it, and we're going to put in the correct answer, aqueous. Good. Hey, that's it, folks. Now you know all of the reactions. Enjoy, and have a good day.